Hello everyone. This lecture will be a continuation from where we left in the previous lecture. The previous lecture we discussed about the velocity analysis of a slotted lever mechanism, slotted lever quick return motion mechanism. In this lecture we will be discussing about the acceleration analysis of the slotted lever quick return motion mechanism. The concept of acceleration diagram is similar to the one that we had discussed in the previous classes. The only difference comes when there is a link which has got both translatory motion as well as a rotational motion. So in the acceleration diagram, like in the velocity diagram, we need to incorporate all these aspects. That is, we need to incorporate the rotational motion as well as the translation motion. As I have told, this is a continuation of the previous question. Now in this question, we have already found out the velocity diagram. Rather, we have drawn the velocity diagram. Now we need to draw the acceleration diagram. And from the acceleration diagram, we need to find the acceleration of the ram D, that is the slider, which is having a horizontal motion. And also, we need to find the angular acceleration of the slotted lever. The slotted lever is OC. Now, like in the case of velocity diagram, if you consider the slider B, it has got rotational motion, or it rotates about point A as well as point O. Also, the slider slides along link OC. So this three motion has to be incorporated in the acceleration diagram also. Already we had discussed in the case of velocity diagram that to accommodate the three relative motion of the slider, we introduce a point B prime which is coincident with point B and lies on link OC. To draw the acceleration diagram, like we had done in the velocity diagram, first we will consider the relative acceleration of point B with respect to A, and then we will try to find the relative velocity or relative acceleration of point B prime relative to O, and then we will represent the acceleration of the slider B relative to B prime. So this is how we will proceed. Now to start drawing the acceleration diagram, first, as the usual procedure, first we need to locate the fixed point. The fixed point is OA. In the acceleration diagram, it will be represented as O prime, comma A prime. You can locate point O prime, A prime near to the acceleration, near to the space diagram. And then first we will consider the crank. The crank here is the link AB. In this link AB, we will start locating the acceleration of point B relative to A. Before locating the acceleration of point B relative to A, first we need to do some calculation like usual. We know that the acceleration of B relative to A will have two components of acceleration. One is the tangential component of acceleration, which is given by alpha into r, where r is the length of the link. And in this question, since the angular acceleration is not given, it can be assumed as 0. That means the crank is assumed to undergo an uniform angular motion. And now regarding the normal component of acceleration, it is given by the formula v square by r, where v square is the velocity of B relative to A that you can get from the velocity diagram, and then divide that with the length of the link. You get this value 23.56 meter per second square. And to represent it in the acceleration diagram, it may be difficult. So what you can do is you can divide this by a scale factor of 5. From point O prime A prime, you have to draw a line parallel to link BA downwards, because the direction of the normal component will be towards the center point, and the center point here will be A. So from point O prime A prime, you draw a line parallel to BA in the downward direction. The length of the line, that is O prime A prime B prime, this line will be the magnitude of the normal component of acceleration, and the end point will be B prime. And since the acceleration of B relative to A does not have the tangential component, the normal component will be same as the absolute component of absolute acceleration of B relative to A. So you please label as I have done it. Now in the acceleration diagram, we need to represent the relative acceleration of B prime with respect to fixed point O. As you know that B prime is the point that is assumed to be coincident with the slider B and lies on link OC. So now we will try to represent the acceleration of B prime relative to O. For that, we need to do a calculation. That is, we need to find the tangential component of acceleration of B prime relative to O and normal component of acceleration of B prime relative to O. Regarding tangential component of acceleration of B prime relative to O, that is given by the same formula, alpha into R. But in the question, the angular acceleration of B prime relative to O is unknown. So that means for the time being, we will not be able to calculate the tangential component of acceleration of B prime relative to O. Now we will try to calculate the normal component of acceleration of B prime relative to O, that is given by the formula V square by R, where here the velocity is the velocity of B prime relative to O, that can be found from the velocity diagram, and that is divided by the length of the link, that is the length of point B prime and O. Okay, so that is given by the value 5.61. Since in the previous case also the normal component was divided by a scale factor, that means this 5.61 should also be divided with the scale factor of 5 and should be represented in the acceleration diagram. To represent it in the acceleration diagram, what you have to do is from point O prime A prime, you have to draw a line parallel to link OC. From point O prime A prime, you draw a line parallel to link OCO, and it should be directed towards the center point. Here the center point is point O, so the direction of that line should be downwards. So from O prime A prime, you draw a line downwards, and the length of the line will be the magnitude of the normal component. Okay, so the length will be the magnitude 5.61. You please make sure that it should be divided by the scale factor of 5. The end point of that line is indicated as X, and again I remind you, since we are drawing the component, you have to draw by dotted line. So since now we have located the normal component of acceleration of point B prime relative to O, now we need to represent the tangential component of acceleration. As we know, we don't know the magnitude of the tangential component of acceleration, but we know that the line of action of the tangential component of acceleration will be perpendicular to the normal component of acceleration. So what you do is, from point X, you draw a line perpendicular to this line, that is line O prime x. Okay, so from x you draw a line perpendicular to line O prime x, and you can extend this perpendicular line. You can extend this perpendicular line on either side of x, and also please note that this perpendicular line should be drawn using dotted line because this is also a component. Now you can see that regarding the motion of slider B, we have represented the rotational motion of B relative to A. Also, we have represented the rotational motion of the slider B relative to O in the acceleration diagram. Now, we have to consider the translation motion of slider B along link OC. So that is what we are going to do. Now, for representing that translation motion, what we actually do here is we actually represent the relative motion of the slider B with respect to point B prime. That is what we are going to represent in the acceleration diagram. Now we'll see how to represent the acceleration of slider B relative to B prime. Regarding representing the acceleration of B relative to B prime, here is where there is a slight change in the procedure that we usually follow in the case of acceleration diagram. One important change is, since B prime is a fixed point, that is why we are going to represent the acceleration of B relative to B prime. In the acceleration diagram, acceleration of B relative to B prime is represented as B double prime B prime. Usually when you locate a acceleration diagram or when you locate a vector in the acceleration diagram, we usually locate it from the point that we already know. But in this case, B double prime is a point that is unknown to us. The point that we know is B prime. So only in the case of representing acceleration of the slider relative to fixed point B prime, we do in the reverse way. That is, we know the ending point. From the ending point, we will try to locate the starting point. Only in this particular case, we do this procedure. In all other cases, we will go for the option where we know the starting point. From the starting point, we will try to draw the vector. Okay? So please keep this in mind. This is one of the change in the procedure from the usual procedure. Now to represent the acceleration of the slider B relative to the fixed point B prime, we need to find the magnitude of the two components. Similar to the previous cases, here also there are two components of acceleration. One will be along the link OC and the other will be perpendicular to link OC. But we don't call those two components as normal and tangential component. Instead of that, we call the tangential component as something known as Coriolis component of acceleration. And the normal component will be termed as normal component itself. So the change in name only comes regarding the tangential component. Now this term Coriolis component you might have learned in your mechanics course. In the case of rigid dynamics of rigid body, you might have encountered it, and that is applicable to any object which is having motion, both translation and rotational motion with respect to a fixed point. So it is associated to the acceleration of any object which is having both translation and rotation. Like here, the slider has got both translation and rotation. In that context, Coriolis component of acceleration comes. Now we'll see how to find the magnitude of Coriolis component of acceleration and the direction. Once we can define the Coriolis component of acceleration, then the normal component will be perpendicular to the Coriolis component. Regarding the magnitude of Coriolis component of acceleration, it is given by the formula 2v omega. We are going to find the Coriolis component of acceleration of the slider B relative to B prime. Then the formula will be 2 into velocity of B relative to B prime, that can be obtained from the velocity diagram, into angular velocity of link CO. Angular velocity of link CO has to be found out from the velocity diagram, that is through this formula V equal to R omega. In this formula I have made a mistake. Okay, from this formula you will get omega equal to V by R, where V is the velocity of C relative to O that we can get from the velocity diagram, and instead of omega CO it should be CO. Okay, please consider this change, consider this mistake, which is nothing but the length of the link CO. Okay, length of the point CO. You will get the angular velocity of link CO as 3.14. Thereby you get the Coriolis component of acceleration as 6.91 meter per second square. So this is how you find the magnitude of the Coriolis component of acceleration. Regarding Coriolis component of acceleration, if you are very much curious enough, I can send you a PDF regarding the derivations or explanation of Coriolis component of acceleration. So those who are interested to go through can go through that head note. Others can just go through this video and just consider this equation. That will be enough. And also you can follow the procedure to find the direction. That will be enough. We have now found the magnitude of Coriolis component of acceleration. Now we will see how to find the direction of Coriolis component of acceleration. For that we will just consider this slotted lever mechanism. In this slotted lever mechanism, the link AB is the crank which undergoes rotational motion in the anti-clockwise direction. So the direction of angular velocity of link AB or BA is in the anti-clockwise direction. Thereby the direction of link OC, or the direction of rotation of link OC, will be also along anti-clockwise direction. Thereby the slider B will undergo motion downwards. Okay, so this arrow indicate the velocity, the direction of velocity of B, okay, relative to the fixed point B prime. Okay, I hope it is clear. Okay, so these are the directions of the angular velocity and the velocity, the linear velocity. Okay. So that this portion, I'm going to enlarge it, and I have drawn it here. So this is the slider whose linear velocity has a direction downwards. So this indicates the direction of velocity of B relative to B prime. And we have seen that the angular velocity of link OC is in the anti-clockwise direction. So what I have done is I have represented the angular velocity in the same side of linear velocity. Okay, so this is the direction of angular velocity of link CO. Okay, now to know the direction of Coriolis component, what you have to do is you have to rotate the velocity vector by 90 degree in the direction of the angular velocity of link CO. Here the angular velocity of CO is directed in the anti-clockwise direction. So that means you have to rotate the velocity vector by 90 degree in the anti-clockwise direction. So this is the direction in which you need to rotate the velocity vector by 90 degree. That means this will indicate the direction of Coriolis component of acceleration of B relative to B prime. Are you able to follow? Okay. So one thing you need to keep in mind is the velocity vector and the angular velocity, the direction of angular velocity should be on the same side. Okay, if it is not in the same side, then it will be confusing for you to find the angular velocity. To find the direction of Coriolis component. Okay, if for example if the angular velocity was somewhere here, then the representation is also correct because it is in the anti-clockwise direction. Okay, but if you draw it here, then it will be confusing for you. So to avoid confusion, what you have to do is you have to represent the direction of angular velocity and the linear velocity in the same side. Okay, I hope it is clear for you. So that is how you find the direction of Coriolis component of acceleration. Regarding Coriolis component of acceleration, we now know both the magnitude and the direction. So with this, we need to represent it in the acceleration diagram. As I had told before, we will be doing it in reverse because we don't know the starting point, we know only the ending point. So what you do is, from B prime, you draw a line towards the left. Okay, so you need to draw in such a way that it is assumed to meet B prime, or it is assumed to, the vector is assumed to end at B prime. So from B prime, you can draw a line perpendicular to link OB. Okay, so from B prime, you draw a line perpendicular to link OB, which is the direction of the Coriolis component of acceleration, and the length of this line will be the magnitude of the Coriolis component of acceleration. Okay, and please you note the notations. Also, the line should be discontinuous and the endpoint can be represented as y. And then once you represent the Coriolis component of acceleration, the normal component of acceleration will be perpendicular to the Coriolis component of acceleration. So what you can do is from y, point y, you can draw a line perpendicular to the line b prime y. Okay, and that perpendicular line can be extended beyond y such that that perpendicular and this perpendicular will meet at a point, and that meeting point is nothing but b double prime. Okay, and once you get b double prime, you can join o prime with b double prime and you can extend. So that is what I have done it here. This line represents the Coriolis component of acceleration, and this line represents the normal component of acceleration of b relative to b prime. And then once you locate b double prime, you can join o prime with b double prime and you can extend. Now we need to locate point C in the acceleration diagram. We know that in the mechanism, C is a point on link OB extended. Similarly, in the acceleration diagram also, C prime will be a point on O prime B double prime extended. For that, you need to use the law of proportion, similar to what you had done in the velocity diagram. Using the proportion, you need to find the location of point C in the acceleration diagram. Okay, so by the law of proportion, we have located point C, that is C prime, in the acceleration diagram. Once we locate point C on the acceleration diagram, now we will consider the ram D. We know that ram D, it has got motion only along positive x-axis. Okay, so that means in the acceleration diagram, from point O prime, you have to draw a line, you have to draw a horizontal line, okay, on either side of O prime. So if you want, you can extend this line on either side of O prime. So that represents the line of action of acceleration of the ram with respect to the fixed point. Now we can consider link CD. Since C is the known point in the acceleration diagram, we will try to find the acceleration of point D relative to C. So first we need to find the tangential, the magnitude of tangential and normal component of acceleration of D relative to C. Regarding the magnitude of tangential component, since the angular acceleration of link DC is unknown, the magnitude of the tangential component is also unknown. Regarding the normal component of acceleration, it is given by the formula v square by r, where velocity v is the velocity of point D relative to C that we can get from the velocity diagram, and we need to divide it by the length of the link DC. You get the magnitude of normal component of acceleration of D relative to C as 1.51. We need to divide it by the scale factor of 5. So what you do is, since we now got the magnitude of the normal component of acceleration, from C prime, you have to draw a line parallel to the link CD. You have to draw a line parallel to the link CD towards the center point C. Okay, so that means from point C prime, you have to draw a line towards the left. Okay, and the length of that line will be the magnitude of the normal component. Once you have the normal component, from the endpoint of the normal component, that is from this point, you draw a line perpendicular to the normal component, and that perpendicular will meet the line from O. Okay, and that point will be D prime. Okay, so this is the final acceleration diagram for the slotted lever mechanism. Okay, so please do the notations as I have done. Okay, and also make sure that all the components should be using dotted line, and the absolute accelerations should be with continuous line. Try to solve the questions that is asked. First, we need to find the acceleration of the ram D. The acceleration of the ram D is obtained by measuring the length between the points O prime, D prime. And this length has to be multiplied with the scale factor of 5. And finally, you will get the acceleration of the ram as 7.75 meter per second square. Now, regarding the angular acceleration of link OB, that is obtained from the tangential component of acceleration of B prime relative to O, that is obtained by the formula alpha into BO. So from this, you can measure the tangential component of acceleration of B prime relative to O from the acceleration diagram, and the tangential component of B prime relative to O is given by the distance between the point X and B double prime. So this line will give you the magnitude of the tangential component of B prime relative to O. That length should also be multiplied with the scale factor of 5 and then divided by the length of the link B prime O. You get the angular acceleration of link BO as 12 radians per second square.